This video is on how to do Hooke's law. So what is Hooke's law? According to Hooke's law, force applied in a string is directly proportional to the extension in the string, right? For example, you have a string right here, and you attach certain mass over here. Suppose that this is the equilibrium condition, and you attach certain mass here. What will happen is this spring will extend from this equilibrium to the certain distance. It depends on the mass, right? According to the Hooke's law, the applied force is directly proportional to the extension. Right here, extension is this mass, right? That is the Hooke's law. Okay, so in this lecture, I'm illustrating how to perform an experiment on Hooke's law. If you click on the link here, this will lead you to this lab. Okay, there are several options to choose. One is the introduction, then velocities, energy, and the lab. We are doing lab, so I'm clicking right here. If you double click here, you will get this window. And let me get data table from this table. Go down to the data table, table 1. It has several columns like mass, STCX in centimeter, load mass in kilogram. You can just convert this gram to kilogram, and then calculate load. We'll do it later. And STCX, yeah. Okay, so right here are so many things. You can see here, this is the mass. Let me put it like 50. We can start from 50. If you look at this table here, it starts from 50 and all the way down 300, right? So going back to the simulation link, click on here to show this displacement natural length, which is the equilibrium position of this spring, and then mass equilibrium, this line. You will see this black line later. Okay, so this is the spring constraint. You can set this spring constraint like anywhere here. Keep it as it is, because you don't have to move this one, so that the material we are using will be same throughout the experiment. We are not changing the material all the time, right, for doing this experiment. So same thing applied here. Acceleration due to gravity should be 9.8. This is for all. If you move this one, it will show something else. That's why keep it like 9.8 meter per second square, and the damping, let's say no. Okay, so here is the mass. So here is the length measurement system. You can bring it here and align somewhere here, right, so that we can measure the extension, that is the length of the displacement of this spring. So we have mass here. To change this, okay, here it's changing, right, so that moving this cursor will change the mass. Let me bring it here, grab it, and put it here. Okay, it will oscillate, and the energy of oscillation is showing. Kinetic energy, potential energy is changing all the time, but we are not worried about these potential and the kinetic energies. So we stop it so that we can have a displacement measurement, right? For example, right now, if I look at here, it's about 10 centimeter. Yes, this is 10 centimeter, and 11, 13, 14 centimeter, right? So let me write down 14 centimeter. Extension is the 14 centimeter. Mass is already there, right? So this is the one data. Let me check it back again, whether it's in centimeter. This scale is in centimeter. This is 10 here. If this line matches with this big line, that is 15, but this is here, so it means it's 14. Okay, okay, so going back to the table, now you have the extension X and mass, right? You can convert this mass, which is 0.05, right? In kilogram, just divide by, if you divide this number by 1000, you will get this one, of course, right? If I'm wrong, do your calculation. Okay, just divide this one by 1000. That's the way how to convert from gram to kilogram. And getting load, weight is mg, right? What is m is this one. What is z? 9.8. So what I'm doing is 0.05 multiplied by 9.88. It will give you some value here. Write it down in this table. Don't show the calculation right here. You can do somewhere else in the calculator and write down just a value, the single last value that we get after multiplying this number with 9.8. Okay. So similarly, we can convert this number into meter. If you divide this one by 100, you will get 0.14. Okay. So in this way, we have done one data. Let's go to the second data. So second data will be 100, right? Mass is, you just increase this one all the way to 100. Let's set 100. This is 100, right? Stop it. Now this is 24. Let me write down 24 here. Okay. Similarly, let me take all the data. Then 150. Let's go 150, right? Stop it, and it looks like 34. Okay, let me write down 34 here, right? And 200, increase all the way to 200. So what is there right now? 40, 41, 42, 43. I see that is 43. Let me write down. Take year data, right? 43. Okay. So again, go back. 250. 250. It's now 50, 51, 52, or 53. Let me write down 53. Okay. 50, 52 is between. I'm not guessing number. Okay. And then again going back and final data, which is click on here and getting this number is about 61. Okay. So 61. So I have a complete table that I have all data, and I can now convert into kilograms, which is 0.24. No, 0.024, right? Similarly, now I'm converting mass here. And if you divide this number by 1000, 2 zeros gone, 0.1, right? 0.1. Similarly, how much is this? This is 2 zeros gone, then 0.15, right? Similarly, this is 0.2. Similarly, this is 0.25, and this is 0.3. Okay, so these are masses. These are masses in kilogram. So similarly, we have extension here, 0.24, 0.34, 0.43, 0.52, and 0.61, right? I'm just dividing these numbers by 100 to convert centimeter to meter. Okay, so similarly, if you multiply all these things by 9.8, you will get this row, which is the load. These are two things we need to know, which is the load weight. Weight means the force, right? Because of that force, that weight, the string is extending. There is the extension or displacement in this string that we call x, right? So you have force, which is N, represented by N, and you also have stress X. So if you look at this data, you can use 9.8. Just for simplicity, let me round it just to show you how to get data. I'm not calculating. But don't use 10, okay? Use 9.8. I'm just using 10 so that I can calculate in my head. So it will be, this number will be 0.5, right? And this number will be 1 multiplied by 10, right? This number will be 1.5. This number will be 2. This number will be 2.5 multiplied by 10. This number will be 3. Okay. So if you look at this data, when you increase the force, we are increasing force from here 0.5 to 1, 1.5 to 2.5 and 3 and so on. What we are getting here is extension is also increasing accordingly, right? 14 meter, 24 meter by almost by 10 centimeter at a time. We are increasing load by the same proportion, right? By 50 grams. That's why if you see the consistency, right? That means increasing here, this column, and increasing here. What does that mean? That is force applied is directly proportional to extension. So this is the x-axis, and right here is y-axis. So put this force along y-axis, which is N. You can go to the Excel and draw this data, and x-axis along x-axis will be the x, which is this x extension, and you will get some line which is straight line, y equal to x plus b. Okay, so this verifies the Hooke's law. If you don't know so much, you can calculate, from there. One more thing I have to tell you is, once you know mass and this force and the stress, you can find a spring constant. So what is the spring constant? From Hooke's law, F equal to kx, right? This k is the spring constant. So you have value x here from your this table, data table 1, and you have x, all these x, right? And you also have mass, force, which are these, right? For example, if you put 0.5 instead of F, and here value of x is 0.1014, then you will get k equal to 0.5 divided by 0.14, right? 0.14. So from here you will get the constant, that is spring constant. Okay. Similarly, once you know the spring constant, if some masses are on, you can find the mass as well. So going back to the lab manual here, yeah, we have done data analysis things and the graph, how to plot the graph and so on. That's all. Then you can read all these questions and answer these questions. Okay.